We're now going to learn how to solve a Bernoulli differential equation. And it's a Bernoulli differential equation. If it looks like this, it looks just like a first order linear differential equation, except, oops, we have a y to the n, which makes it nonlinear. Now, p of x and q of x are continuous functions on the interval from a to b, and n is a real number. However, if n is 0, of course, you get y to the 0, so that is just a first order linear differential equation. If n is 1, then you just got a y there, and we can bring all this to the left-hand side and factor the y out of there and solve it with variable separable.
For all other cases, we're going to make a variable change. The first thing you want to do is divide the Bernoulli equation completely through by y to the n, then make the variable change v equal y to the 1 minus n, find dv dx, and then solve that for y to the minus n dy dx that you're going to substitute right here. Y to the 1 minus n is v, and notice this differential equation can then be put into a form that is first order linear in v and x, which we know how to solve, and then substitute back to get the variable y.
Our objective tells us to solve a Bernoulli differential equation.
Let's solve this Bernoulli equation with n equal to 2.
This equation looks like a first order linear differential equation except for the y square right here, which makes it a Bernoulli differential equation. So the first thing we do is divide through by that y square, y to the n right here with our n equal to 2. We divide through by it and we get this form right here. We let v equal y to the 1 minus n or 1 minus 2, so we get v is y to the minus 1. We take the derivative of that with respect to x, so we have dv dx is minus y to the minus 2 dy dx, or we have minus 1 over y squared dy dx. And you'll notice that 1 over y squared dy dx is equal to minus dv dx. And that's what we substitute right in for here. And we're going to substitute for 1 over y, v, and we have this form you see right here. So the next step is to get us a plus 1 in front of the dv dx. We multiply through by minus 1, and now we have a first order linear differential equation with an integrating factor mu equal to e to the integral of p dx, e to the integral minus 1 over x dx, or e to the minus log x. That's e to the log to the base e of x to the minus 1. And again, e to the log to the base e of a quantity is just that quantity, so we get 1 over x here for our integrating factor. Multiply the equation through by 1 over x, and we get the form that you see right here. Notice it's 1 over x dv dx minus 1 over x squared v minus x. And if we've done everything right, we have the derivative of the product on the left. I think of this as just, hey, take this term right here, 1 over x dv dx, and eliminate the derivative with respect to x, 1 over x v. If I did this correctly, I've got the derivative of that product. So we check here. First times derivative of the second, plus second, derivative of x to the minus 1 is minus x to the minus 2. And so we have the derivative of that product is equal to minus x. Now we integrate and get v over x is minus x squared over 2 plus a constant, or we multiply through by x and get v is equal to minus x cubed over 2 plus the constant times x, but v is 1 over y. So in this next step, we've got us a common denominator here. We're going to replace the 2c1 with just some other constant c, as it says here. And then we're going to take the reciprocal of both sides, and we'll have this solved for y. Y is equal to 2 over x times the quantity c minus x squared. Now I should mention there's also the trivial solution on all of these, because if y is 0, you get dy dx, of course, is 0, y over x is 0, and x squared y squared is equal to 0. So 0 is equal to 0. But that trivial solution is of no use to us in engineering, so we don't generally worry about it. Well, in our second example, our n is minus 2. And so we divide through this time by y to the minus 2, or we're really multiplying by y squared, and get the form that you see right here. We let v equal y to the 1 minus n, so that's y cubed, dv dx, 3y squared dy dx, or y squared dy dx is 1/3 dv dx. And that's what you see right here. V was y cubed, and that's equal to e to the x. So now we have a first order linear differential equation. We multiplied through by 3 there to get us a 1 in front of the dv dx. E to the integral p dx, so we get 3 dx to integrate, which gives us just 3x, or e to the 3x for our integrating factor, which we've multiplied through by right here. And again, if we did this right, we can take this term right here and get rid of the derivative with respect to x, and we would have the derivative product e to the 3x times v. So let's check it. First times derivative of the second, that's what we have for the first term, plus second v, derivative of e to the 3x is 3e to the 3x. And so that's the derivative of that product. That's equal to what we see on the right. We're going to integrate, and we get e to the 3x v is equal to the integral of 3e to the 4x dx. So we integrate e to the 4x dx and get e to the 4x over 4 times the 3 there, plus our constant of integration. So we have v, if we divide through here by e to the 3x, we have v is equal to 3/4 e to the x plus a constant e to the minus 3x, but v was y cubed, and now if we take the cube root of each side, we get this form that you see right here. We could get a common denominator here and get this in the form, if we get this as 8 over 3x, we would have 6 e to the x plus 8 times a constant over e to the 3x. We wanted to get the 8 down there because we can take the cube root of 8 and get 2. And so we could get this form right here, but either of these two forms are fine.